where I can maximize. So question 1 says, which of the structures are aromatic? Can I get contribution so it can flow quicker? Is it A, B, C, or D on the first one? Come on, please, don't waste time. We have to do much.
B.
B.
Okay, B is not aromatic. The answer is actually A. If you look at B, these electrons can be transferred. So you really have 4 pi electrons. That's gonna fail the last rule, which is 4n plus 2 equals to 4. If you solve for n, you get a fraction, but this is gonna go with the 4n rule. So this one right here is anti. This is aromatic. You have 2 lone pairs. One of the lone pair takes part in resonance. See how I'm pushing things around? And the other one stays. So here, if you count the number of pi electrons, is 2 here, 3, 4, 5, 6, 7, 8, 9, 10. So test this for 4n plus 2 equals to 10. Turns out n equals to 2. That's a whole number. Of course, it's conjugated. That's why I could draw the resonances. This oxygen right here is sp2 because 1 lone pair took part in resonance. So I only count this as a domain and then the 2 bonds. So 3 electron domains. That gives me sp2. So the answer here should be A. Okay, this would be the answer. I can't write on the web, but for that question with the first set is A. Now, someone give me the answer to the last one. Which of the following structure is non-aromatic? Oh, before we do that, actually, C is anti-aromatic. What about D? Is it aromatic, anti-aromatic, or none? Someone?
Is it non-aromatic?
No, actually it's aromatic. You know, this carbon right here is sp2, and I can draw resonances all around the ring. So everything is flat, trigonal planar. So I expect this to also to be aromatic. So for that first set of question, the answer is A and D. The ones in the middle, they have 4 pi electrons. Those are anti-aromatic. They are planar cyclic conjugated, but they fail 4n plus 2. They pass 4n rule like I showed here. So now let's go to the last set. Which of the following is non-aromatic? What's the answer? Someone?
C?
C is anti. It's 4 pi electrons. D is not. B is not. So actually, the answer to that one was none of the above. Let me see if we had none of the above. Yeah, the answer is none of the above choices. Because the A is aromatic, B is anti, C is anti, D is aromatic, so the answer is F. None of the above choices. Oh, do we have a carpenter? Please mute your mics unless you want to ask a question. So now let's do the next set. Do you have a question on that part, or should we do the next set?
How do you know if it's non-aromatic again?
Oh, yeah. So you know there's 4 rules for aromaticity.
Yes.
Can you list them for me?
Conjugated.
Okay, that should be.
Conjugated.
Okay, go.
So it has resonancy.
Go slow for my lazy old hands. So conjugated, then what?
Cyclic compound.
Okay, it's a ring. Then what?
Planar compound. So that means all of them are sp2 carbons.
Yes, or at least you have conjugation. Yes, and then 4n plus 2.
4n plus 2.
Okay. So now,
Number
if a structure fails a combination of the first 3, or one of the first three, then it's non-aromatic. So it turns out not to be planar, it's non-aromatic. If it turns out not to be conjugated, it's non-aromatic. It turns out not to be cyclic, it's non-aromatic. If it fails the 3 or 2 of these, it's non-aromatic. Is that clear?
Yes, thank you.
All right. For anti, it will pass 1, 2, 3, but fail the fourth one. Instead, it's gonna pass 4n equals number of pi electrons. That would be for anti. All right, so I think that's clear. Let's look at I'm just gonna go down. That was aromatics. Let's look at 10. Okay, there you go. So this is the questions for 10. And the question says, so let me open up the first one. And give me some room. So identify the type of reaction that will provide the major product in the reaction represented below. Contribution. So now, let me guide you because of interest of time. I want to do as much as I can. So what you're seeing first of all is that this is a secondary alkyl halide. The alpha carbon bearing the leaving group is bonded to 2 other carbons, so it's secondary. So it could either go SN1, E1, E2, SN2. That's not helping. So we go to the arrow. I see a reagent given. So someone give me ideas. What do you see? What do you conclude about methanol? Someone? What does that tell you?
It's protic.
I agree. Tell me one more thing. Is it a weak base, strong base, weak nucleophile, strong nucleophile? Huh?
It's weak.
Yes, it's weak. It's both weak base and weak nucleophile. Now, if you take it as a weak base, then you're thinking E1. But I told you E1 only wins when your starting material is an alcohol. That's not an alcohol. So in this case, we're going to take it as a weak nucleophile. And it's SN1 that does weak nucleophiles, that uses weak nucleophiles. Now look at your product. That's a huge hint. You have a racemic mixture. The reaction that gives you racemic mixture and undergoes substitution is always SN1, never SN2. So the answer here is B. You are seeing Cl is converted to the methoxy. Plus you have two products. It doesn't always give you 2, but in this case it gave you 2 because that's chiral center. You substituted, so it cannot be elimination. It cannot be A. It can't be D. So it's either B or C. Now it's not C because this is a weak base. SN2 prefers strong nucleophiles. If this was CH3O-, the presence of a negative charge, that implies strong nucleophile. Then you will think SN2 because your products show substitution. That's how you tell. Do you have a question on that before I exit out? This is one of the poorest done question in your exam 3. One of the questions that was not well done. Let's pull up one other version of it. Okay, so now in this case, you still see you moving from a Cl to a Cn. Someone tell me what's also shown on the product versus the reactant. What else do you see?
Sodium? Oh, wait, what was the question?
What else do you see comparing the reactant and the product? Spot the difference.
A substitution.
Okay, substitution, and then spot the difference. What else is happening?
It's inverted?
Yes, and which reaction does inversion? It has to be SN2 because the nucleophile attacks from the back. You see, to me, I would say the test was very, very, very doable. In fact, extremely doable, because all the clues were given, especially in this part. Usually, I would ask you to draw mechanisms, but we were not in class, so you are happy not to do mechanisms. Okay, so now what I mean is this. So take that molecule like this, and then look at the arrow. You're given NaCN. I told you whenever you're given such, know that the metal is just a spectator ion and is usually positively charged. So the atom element next door will get a negative. And you know this is a negatively charged species. Obviously, it's a strong nucleophile. And in class, during phase instruction, I told you, was it in class or just after phase instruction? I told you whenever you see negative species, I think it was online. Whenever you see the negative charge species, you know that's a strong nucleophile. And in fact, Cn minus, SH minus, Sr minus, N3 minus, these guys will always do SN2. Always, and never E2, because they are never bases. They are never bases. They are always strong nucleophiles. So the nucleophile will attack from the backside. That's what SN2 does. And that's why you get inversion. Okay? My interest is just to show stereochemistry regardless of my drawing. That's why we show inversion, because of the back attack. And I know it's SN2 again because I have a strong nucleophile, the nitro. Do you have a question on that? Answer here is C. You have a question on that? No? Okay, so let's look for the next version of question. I'm just gonna go down as we go. It could be very similar to what we just discussed. Okay, so let's do this one. So it says identify the type of reaction that will provide the major product in the reaction represented below. Someone give me an input. What do you think?
E1.
Okay, is there any other input? All right, so now we are definitely making double bonds, so it has to be elimination. So the substitutions are out. So it's either E1 or E2. Now look at the arrow. Do we have a strong base or a weak base? Someone, do we have a strong base or a weak base?
Is it strong?
Yes, then it has to be E2 because we know it's strong because that CH3, let me pull it over so you can look read side by side. I wish I brought my mouse for this old computer. Okay, let's see. Minimize it. So the CH3, what's provided on the arrow, it's CH3, O and A. Like I said before, assume the metal is not there, you put a negative charge. CH3O minus. A strong base will have a negative charge on it. Most of the time it will have a negative charge on it. This is an alkoxide. Alkoxides are always strong bases. This is stronger than its conjugate acid. That's a weak base. So this guy will do E1. But this one, okay, this one will do E1 or SN1 because it's weak base, weak nucleophile. This one is a strong base, strong nucleophile. So it can do E2 or SN2. But looking at the question, you're making double bonds, pi bonds, so it's elimination. So the answer has to be, it has to be E2.
E2.
Yeah. So the answer is C. All right. I think you're getting the reasoning. That's the main thing. That's my software that's recording popping up. You're getting the main idea. Okay, so now let's pull another question. Down here, we have one that's interesting. This is another question that, for those who got this random question, most of them did not get it right. I don't know why, but I gave you the clue. That's an alcohol, right? Alcohol converted to a double bond. This is dehydration reaction. So it has to be what?
Elimination.
It has to be elimination. Now, do you see a strong base there? Because E2 will always want a strong base. Do you see a strong base there?
Yes.
No, that's a strong acid. It's sulfuric acid. Sulfuric
Oh,
acid.
yes.
So that's a huge clue. You would have known that this is giving me a double bond. Well, it's an elimination, and it's actually specifically dehydration because you're losing water. But I'm not given the strong base. I'm given a strong acid instead. Strong acids are weak bases. So E1 likes weak bases, so we go with D. Okay, so if it shows up again, if an alcohol shows up again with sulfuric acid or phosphoric acid and heat, know you're going E1. Because the final is just usually a hybrid of what you guys have done from exam 1, 2, and 3. I started with 3 today because that's usually the worst poorly done test. Okay, so let's see. But the class average apparently was a 71, which is like 20% higher than normal. Usually the average is between 54 and 57 for exam 3, whenever we have in class testing for exam 3. Okay, now let's see. Let's do, let me go on the opposite side. Can I have maybe question 6, question 5? I need a pen so I'll know what I worked on. I'm juggling around just based on the time we have. Okay, so question 5, it shows 2 of them. Let's see what it's asking. All right. Which of the following is the best solvent for SN2? Someone give me your answer and give me your reasoning.
Acetone.
What's your reasoning? I agree it's acetone.
A product.
I agree it's a product. If you look at water, okay, so let's see. Lost my stylus. So if you look at this, the choices given, you're given H2O, you're given, okay, that will do. So if you look at the structure of H2O, this is protic. For those who've forgotten, protic solvents will have hydrogen bonded either to oxygen, nitrogen, sulfur, or fluorine. No, sulfur is not one of them. I think oxygen, nitrogen, and fluorine. So water is protic. Acetone, on the other hand, has this structure. You see, the hydrogens are not bonded to any of these 3 elements. So this is aprotic. And SN2 will love aprotic solvents because they don't compete as nucleophiles. Here, water can take the role of a nucleophile and compete with the nucleophile used in SN2. Of course, ethanol is protic. Acetic acid, the active ingredient in vinegar, is also protic because of that hydrogen. So that's why the answer was acetone for that part. If you have a question, just unmute your mic and ask as we review. So let me do the next one. It's similar to what we just asked here. So it says, which of the following solvent is the best for SN1? What's the answer? Unmute your mic. Whoever, just unmute your mic and tell me.
Isopropanol.
Isopropanol will not. Which of the following is the best solvent for SN? Oh yeah, it's isopropanol, you're right, because it's asking for the best solvent. It's isopropanol, and it's because isopropanol is protic. That's an isopropyl group, and then you put OH, that gives you isopropanol. It's protic. The rest are not. A, hexanes, 6 carbons. You only have carbons and hydrogens on this structure. B, cyclohexane, same story. You have, that's a hydrocarbon, hydrogen and carbons. C, toluene, an aromatic ring. All carbon hydrogens. And then of course you know what benzene is. Hydrocarbon. So this is the best because it's protic. SN1 likes protic solvents because these lone pairs tend to stabilize the carbocation intermediate. That's why it loves protic solvents. Okay, let me just minimize that one. Let's pick up another random. Number 4. Yeah, this one was an interesting one, but most of you got it right. How many pi electrons are in the structure? Someone tell me.
6.
Are you counting those pi electrons on the nitrogen on top?
No.
Correct. Don't count those ones because I gave you the clue to identify the number of pi electrons. If the nitrogen, oxygen, or sulfur is doubly bonded and it has a lone pair, the lone pair that is going to be there attached on that element, like here nitrogen is doubly bonded, that lone pair is not going to be counted as a pi electron, as pi electrons. But here, down here, the nitrogen is singly bonded to the carbons and the hydrogen. So you know that this lone pair should take part in resonance, either going to the right or to the left. So you count these electrons as pi electrons. That's why this nitrogen here is sp2 hybridized. There's 3 bonds to be counted as electron domains. We don't count the lone pair as an electron domain because it's not available. It keeps on going around the ring. So you have the 2 electrons in the lone pair and you have the 4 electrons in the pi bonds. You have a total of 6. Okay. Now what of in this one?
Is it 6?
It's still 6. So you choose one of the lone pair on the oxygen that's going to take part in resonance. Again, you don't count this guy here because the lone pair is sitting on a nitrogen doubly bonded. So whenever the heteroatom, remember heteroatom could be a sulfur, an oxygen, or a nitrogen, and a phosphorus. So whenever the heteroatom on the ring is doubly bonded, at least doubly bonded, and it has a lone pair, that lone pair of electrons will not take part in resonance. It's not pi electrons. In fact, those electrons reside in sp2 hybrid orbital. But this lone pair, for example, here is on top of the ring. That's in the p orbital. This lone pair here will be in the sp2 orbital. So this one does not take part in resonance. The top one will take part in resonance. Takes part, excuse my writing, takes part in resonance. Okay, so we count it as pi electrons because they're in the p orbital. So 2 pi electrons in the lone pair, and then you have 4 of them in the 2 pi bonds. So you have 6 pi electrons total. Okay, so what of the last one? Let's see, not that one. What of this one?
Ten?
Okay, I have an answer of 10. Let me see if I can redraw it so we see where the 10 are. Can you direct me where you saw the 10?
I just counted all of the double bonds as 2 pi electrons each.
Okay, 1, 2, 3, 1, 2, 3, 4, 5. You did not know that we have lone pairs here?
Oh, that's right. No, I didn't count those.
So it's 14. That should have 14 pi electrons. You have 10 in the pi bonds, and then, you know, the nitrogen has to maintain octet rule. That's how I know that there are 2 pi electrons there. You know, if you just leave it like this, it means this nitrogen has 6 electrons out of the 3 single bonds. That's how I know we are missing 2 lone pairs. So that's how you know to show them and then count. So when it comes, let it not get you. Okay, so good. So we go back. I think we're gonna go back to some of the. Which question was that? I think that was for. I'm gonna go random. Let's see what this 20 is.
So if an atom has 3 sets of lone pairs, would you still only count one of the pairs of lone pairs?
Yeah, you just use one.
One
Yeah,
of them,
you
okay.
never use more than one. Just use one. Okay, this is one of the questions that was not well done. What reaction profiles would follow the represented energy profile diagram? Okay. Someone give me a contribution.
SN1?
Okay, what's your reasoning? I agree.
Because it has the 2 transition states and an intermediate.
Correct. The intermediate is here, which will be the carbocation. I write I for intermediate, the carbocation, and then you have TS1 and you have TS2. Overall, the reaction is exothermic, just for the review purposes. But now, because of the presence of the intermediate, I expect to be SN1. Which reaction competes with SN1?
E1.
So the correct answer here was D. It could be either SN1 or E1 because the products are not shown for us to know whether we are making pi bonds or substituting. So it's either E1 or SN1, not just SN1. Okay. And then we have this one here. Let's see if it's gonna open. So what about for this one? One transition state, it has to be either SN2 or E2. Those ones are concerted reactions. You know, if there's no question, I keep flowing. I'm assuming I'm doing a good job reviewing. I'll keep going. Let me note down. I've done 20. Okay. So now we go. Let me choose 14 and see what is inside 14. Which of the following is a false statement? Bimolecular elimination reactions lead to inversion of configuration. True or false?
True.
It's false.
Oh.
The reason being, with elimination, you don't get inversion. You're making pi bonds.
Okay, so it's only the bimolecular substitution?
Correct.
Okay.
Correct. Which means now B, C, and D should be correct. Unimolecular and bimolecular elimination reactions form new bonds. Yes, Those are eliminations that make new pi bonds. Unimolecular substitution and unimolecular elimination reactions happen via formation of carbocation intermediate. Yes, that's what we just drew here. Bimolecular elimination reactions follow anti-coplanar rule. Yes, for those who've forgotten what that is, and I think it's one of the questions, is where you want the beta hydrogen to be taken out by base to be 180 degrees apart. So if the base takes out the hydrogen, you want to make a double bond while these guys are 180 degrees apart. So yes, the answer was A for that. Oh.
I have a question back on the counting pi electrons.
Yes.
If we have a double bond, it's 2 electrons, but if there were a triple bond, would it be 4 electrons?
Correct. But only 2 of the 4 of the triple bond will take part in resonance.
Okay, so you would only count it as 2 pi electrons?
No, you still count them because you don't know which of those 2 pi bonds will take part, right?
Yeah.
So you still say you still count. You see, overall, if you're asked how many pi electrons, you just have to count all of them. But now, if the question is saying how many pi electrons are taking part in resonance, then you'll have to consider only 2 of the 3 of the 4.
Okay, thank you.
Good question there. Okay, now let's see. 13. Here comes trouble. Let's see. Which of the following molecules cannot easily undergo bimolecular nucleophilic reaction? Input, someone. Can we have a boy child represented here, please?
Structure A?
Structure A? Okay, let's see. A is that a primary, secondary, or tertiary? Alkyl halide.
Tertiary?
Okay, now we are asked about the bimolecular nucleophilic reaction. So we know, I think the hidden question was, does the student know the trend? Methyl halide is more reactive than primary than secondary tertiary. In fact, most of the time, this is a no reaction. So we are looking at bimolecular nucleophilic reaction, and this is the trend of SN2, bimolecular nucleophilic reaction. So which one cannot? It has to be the tertiary. A is tertiary. How do I know it's tertiary? Of course, looking at just that part of the ring, I see that I have 3 carbons bonded directly to the alpha carbon, which is the carbon bonded to bearing the leaving group. So this is tertiary, just carrying this lower part. So that should be the answer, because the nucleophile cannot attack it from the backside because the backside is crowded by the carbon groups. Backside of the leaving group is crowded. So yes, the answer should be structure A. Structure B is primary, that can do it. Structure C is secondary, it can do it. Structure D is secondary, it can do it. I wanted to work on this. So which of the following molecules below cannot undergo bimolecular electrophilic reaction? E2. Which one will not do E2?
Would it be the same structure? Structure A?
Structure A? No, structure A will do it. I think the hidden information is which of the following does not have a beta hydrogen. That's another way of asking it. Which one does not have a beta hydrogen? Because the one that does not have a beta hydrogen will not do E2.
So structure B?
It has to be structure B. You're right. Now, I think it might be tough for you to see that structure B lacks beta hydrogen, but I'm going to sketch it down here on my little board. I'm drawing structure B. See, that's why I wanted to download this file. Then I could draw directly on it, but technology refused. So beta hydrogen sit on neighboring carbons to the alpha carbon. That's alpha, this is beta. So if you look there, you have a carbon, you have a carbon, you have a carbon. So this carbon right here does not have a hydrogen. So there's no beta hydrogen. You know, for you to do E2, you have to remove a hydrogen. Like we removed this beta hydrogen, you have to remove a hydrogen to make a double bond. So the answer is structure B. Which of the following will react slowest?
B.
With ethanol. So if it's saying slowest with ethanol, then you are thinking either SN1 or E1. SN1 and E1 go through formation of a carbocation. Now think again, because the answer is not B. So which of the following will give you the least stable carbocation after the leaving group falls off?
C?
Yes. If the Br falls off, you get a primary. You know, the more substituted the carbocation, the more stable it is. So C gives you a primary, D gives you a secondary, because that carbon is bonded to two others, you get a plus charge there. B for boy, gives you a tertiary, because you get a carbon there, and carbon there neighboring the C plus. This would probably be the most reactive. And then A will give you a secondary. So the answer is C. It's going to react slowest. Let's stop there, and then I'm going to send you a file. I'll request you, I know you're busy, but I'll request you to go over the past final exam. Before we meet on Thursday, we'll go over that exam, and we'll go over, I'll choose some of the questions from this exam 3 that I know were least well performed. And I'll send this recorded video on Moodle under the final tab. All right. Bye, people.